So we're into section 4.4, the Fundamental Theorem of Calculus. We're in chapter 4, which is again integration, and we're going to start putting things together in this section. So our objectives are to use this fundamental theorem of calculus to help us evaluate a definite integral, make it a little easier to do, to understand the mean value theorem and how it applies with integrals. And using that, we can find the average value of a function on a closed interval. Then we'll get to the second fundamental theorem of calculus, and finally use that to start talking about the net change theorem. So, as we've been looking at calculus, we started with differential calculus, which was based on the idea of the tangent line problem. Then we got to integral calculus, which we're working on now, which is based on the area problem. And these two different problems, these two branches of calculus, are connected by this fundamental theorem developed by Isaac Newton and Gottfried Leibniz pretty much concurrently and independently. And that's why people argue about who came up with calculus. Who really cares? I don't know. Well, I suppose somebody does. But basically it says that differentiation and definite integration are inverse operations. So here is the fundamental theorem of calculus. It says that if small f is a function that is continuous on this closed interval, and capital S is an antiderivative, because of course there's an infinite number of these, we can pick any antiderivative we want, then the definite integral from a to b of f of x dx is the antiderivative at b minus the antiderivative at a. So we can use those antiderivatives to find these definite integrals instead of having to do a limit of a sum. Woohoo! Right? So as we're using this, again, we don't have to use the limits. This notation is commonly used that when we say instead of f of b minus f of a, we'll often just say f of x and put a vertical line or a square bracket and say a to b on there. So if we're looking at the integral from 1 to 3 of x cubed dx, the antiderivative or an antiderivative, we don't need all of them. We just need any antiderivative. X to the third gives us x to the fourth over 4. Come back here. So when we evaluate that from 1 to 3. So we plug in 3, we get 3 to the fourth over 4. Plug in 1 to the fourth over 4. Take the difference, we get 20. Now what about C, which I was making such a big a deal about in an earlier section? When we're doing an antiderivative, we always need C. That gives us the family, all of the values. But look, when we're evaluating it at B and then at A, we get f of B plus some constant minus f of A plus that same constant. We ended up with C minus C. They cancel out. It doesn't matter what the constant is, since it's involved in both at evaluating at A and evaluating at B. That constant always drops out, so we don't need to worry about the constant of integration when we're doing definite integrals. But when we do the indefinite, don't forget them. Okay. So let's give this a try. You might want to give these all a try on your own. You might want to sit through and work through that first one with me and then try the rest on your own. Pause as you need. Whoops. I need to go down here. So in this first one, I'm going to take out my constant. I'm going to rewrite this as x to the 1/2. So that's going to be, why did I say negative 1/2? I don't know. It's been a long week, right? So the antiderivative of x to the 1/2 is going to be x to the 3/2, because we add 1 to the 1/2, and we divide that by 3/2. And we evaluate this from 4 to 9. Well, again, I'm taking a difference. I have this common factor. I can just pull this out. So I'm going to take this and pull it out here, and instead of dividing by 3/2, I'm going to multiply by 2/3. And so I'm going to get 4/3 times x to the 3/2, evaluating from 4 to 9. So that's 4/3 times 9 to the 3/2 minus 4 to the 3/2. So what? We got 4/3 times square root of 9 is 3 cubed is 27. Square root of 4 is 2 cubed is 8. So I get 4/3 times 19 is what's going to give me 76 over 3, which is approximately 25.3, if you like to have it as a decimal instead of a fraction. Second problem, we're just going to dive right into this. Because 2x squared, we can do the antiderivative. We have 2 times x to the 3rd over 3. Plus the antiderivative of 3 is 3x. Again, I don't care about the constant. I'm evaluating this from -2 to 1. I could break those up into the two different ones, but polynomials, they're easy enough to do. So we're going to take this down to, let's just go ahead and plug things in. We have 2/3 times 1 to the 3rd power plus 3 times 1. We're going to subtract from that 2/3 times -2 to the 3rd power plus 3 times a -2. So, what's 2/3 plus 1 plus 3 minus -2 to the 3rd power is -8, -16, so that's going to be plus 16 over 3. And then again, we're going to have minus, we're going to get a negative here. So we're also going to get a plus on this one. So what we're going to get plus 6. So that's going to give me what? 3 plus 6 is 9. 2 and 16 is 18 over 3, which is 6. So we get an answer of 15. Integral from 0 to pi over 4 of secant squared. One thing, again, I'm going to keep repeating this, reminding you, whenever we are dealing with calculus and trig together, we need to be in radians. So we're going from 0 to pi over 4 of secant squared x dx. And if you remember or look up in your handy-dandy table, the antiderivative of secant squared is tangent. So that's the tangent of x, evaluated from 0 to pi over 4. So that's going to be the tangent of pi over 4 minus the tangent of 0. Tangent of pi over 4 is 1. Tangent of 0 is 0. So we get an answer of 1. Woohoo! So this fundamental theorem of calculus sure helps this out doing these problems. I definitely would not want to do this one by doing the rectangle method and doing a limit. Oh, it just makes me want to cry just thinking about that. I don't know, maybe it's not that bad. Might be worth something fun to do over the weekend, right? Hey, let's try to do the limit there. Okay, sorry. Uh, what about this one here? We don't have an antiderivative of an absolute value. Plus, it's an absolute value. This looks like a composite function, and that sounds like that's going to be problems. Yeah, we're going to look at composite functions next section. Start dealing with that. But let's look at this. This absolute value of 3x minus 6. We know when x is 2, this is 0. If it's less than 2, so, whoops, let's clear this off. So if we think about this graph, at 2, it's going to be here at 0. And then it's going like this. And we want this definite integral, again, gives us the area under the curve, which is this area and this area. We can't deal with the absolute value, but we can come along and say, I can break this up into 2 intervals. Because we said we could do that. We could say this is going to equal the integral from 0 to 2 of the absolute value of 3x minus 6 dx, plus the integral from 2 to 4 of 3x minus 6 dx. But we still have the absolute value. However, on this side, absolute value does nothing, because if x is bigger than 2, this is positive, the absolute value does nothing. So I can rewrite this one as 2 to 4 of 3x minus 6 dx. That we can deal with. On this side, if x is less than 2, this is a negative number, so I take the opposite. Sorry, over here. I get the opposite. So I'm going to get this is going to be the integral from 0 to 2 of the opposite of 3x minus 6. I can get rid of that absolute value by taking the opposite of what's in there, because that's what the absolute value will do here. But we also had a rule that said, hey, the absolute value of the integral of a negative is the same as the opposite of the integral if we switch these limits of integration. So we could switch this instead from 0 to 2. We could say this is from 2 to 0 and do 3x minus 6 dx. And add those two together. One nice thing here is we have the same antiderivative we can use for both of those. So if we look at the antiderivative of 3x minus 6, if f of x equals 3x minus 6, we can make our big F be 3x squared over 2 minus 6x. And we can use those in both cases. We just have to now get this evaluated correctly. So I'm going to start off with this one, and I'm going to say I want 3x squared over 2 minus 6x evaluated from 2 to 0. And I want 3x squared over 2 minus 6x evaluated from 2. Sorry, we're going 2 to 4. So here we're going to first go plug in 0. That one's nice, that's 0. We plug in 2. We're going to go 3 times 2 squared is 4 over 2 minus 6 times 2. That's 12 over 2 is going to be 6 minus 12 is going to be a negative 6. Okay, something's not looking quite right on here. Oh, because it's 0 minus a negative 6, so that's going to give me a positive 6. Now when I go over to this one, I'm going to evaluate it at 4. And so I'm going to get 3 times 16 over 2 minus 6 times 4. And I have to subtract from that. Let's get this up. Well, I'm plugging in 2. When I plugged in 2, I got a negative 6. So I'm going to subtract from this a negative 6. So I'm going to get here 3 times, okay, 16 is 8. So this is going to be 24 minus 12. Okay. I got a sign messed up on here. So that's a 12. Why is this one? No. Scratch that. I'm doing this right. Let's fix this. 16 times 4 is 24. So that's 0 again, minus a negative 6. Gives me 6 again. 6 plus 6 is 12. And hopefully it makes sense that if you look at this, the area under this side is equal to the area under this side because we got symmetry going on here. But sometimes we have to break up these functions when we're going ahead and doing this to make this make some more sense. So let's talk about the mean value theorem here. So the idea here, well, we'll just kind of talk this through. If f is continuous on the closed interval a, b, okay, this says there exists a number in C of the closed interval such that the integral from a to b of f of x dx is this f of c times b minus a. What it's saying is if we're looking, this integral describes the area of this under this curve, that we can find some value on here, some value of c on here where it's going to cover, because the mean value is based that we could make a rectangle that has the same area. That the area that we're overestimating here is the same as we're underestimating here, and those two cancel out. That's the mean value theorem. A little easier to maybe see this and how we're going to apply this. Note, it doesn't help you find C. It just says C exists. It says you can always find that value. But it kind of gets us to this helpful concept, this idea that we can have an average value. You talk about the fact that your f is constantly changing, but we can say what would be my average value, and we can find it by using this idea of this mean value. So the definition of the average value of a function is we're going to take basically the area under the curve, and divide it by the width of the interval, which will give me what value I would need to make that rectangle. And that value would be the average value of f of x. So we're saying having a constant value of this mean value would be the same as our fluctuating value in the long run when we look at the area under both of those curves. So let's kind of work this out and kind of see where it looks like. On this one, we're looking at, to find the average value, we're going to say 1 over 1 minus 0, which is nice, and take the integral from 0 to 1 of 4x cubed minus 3x squared dx. So 1 over 1 is just 1, so I just worry about that integral. I take my antiderivative, and this is 4 times x to the 4th over 4 minus 3 times x to the 3rd over 3, evaluated from 0 to 1. So we got x to the 4th minus x to the 3rd, evaluated from 0 to 1. If we plug in 1 here, we get 1 minus 1 is 0. We plug in 0, we get 0 minus 0 is 0. So for this function, the mean value, the average value, is 0. That was your technically, in the way where, okay, the teacher works through this one, this is an easy one, and then they throw you the nice, nasty one to do. Here, this is easy. See how easy it is? You try this one now. Okay, so I'm not going to do that. Let's just work this through. I'm going to look and see, there's my constant. Well, first, 1 over 3 minus 1. 4 is a constant, so I'm going to pull that out. 4 times the integral from 1 to 3. And then this is x squared plus 1 over x squared. So I'm going to say x squared over x squared is 1. 1 over x squared is x to the negative 3rd dx. That'll help things out a little bit. This is starting to look better already. 4 times 1 over 2 is going to be 2. My antiderivative of 1 is going to be x. X to the negative 3rd, we're going to add 1 to this, which is going to make that a negative 2nd. And we're going to say divide this by negative 2. And evaluate this from 1 to 3. Or 2 times x minus 1 over 2x squared from 1 to 3. So we first plug in 3. 3 minus 1 over 3 squared is let's see. What did I mess up here? Oh, this is a 2 here. So this is going to be a 1, and this is going to be a 1. Oh, boy. Sorry about that. I'm too far into here to re-record this, so we'll fix that error there. So that's not a 2, that's a 1. That makes this much nicer to work again. So this is 3 minus 1/3. We plug in 1, we get 1 minus 1 over 1. 1 minus 1 over 1 is 0. So this is going to give me 2 times 3 minus 1/3 is going to be 8/3. So I get 16/3, which is 5.3 repeating. Finding the average value. You notice all of the mistakes that I made on here were really simple algebra mistakes, so watch out on there. I'm at 25 minutes here, so I'm going to break this video now, and I will finish in part 2.